Alright, so we are starting from here, but remember this slide is extremely long, so we are not going to cover everything in one night for sure, but we'll give a several we'll give several stops. So we'll stop at several points. We'll be like, at this point we'll stop here, we'll do homework 1, again we'll do something, we'll stop somewhere, do homework 2, and the slide will exactly tell you where to stop. That's what I'm saying? Okay, now, so since we are very beginner, let's look at what the microprocessor is. Remember, at this point, we are not looking for the fastest microprocessor of the world, but we are looking for the very basic one which serves the purpose. And also, doesn't matter how fast or how slow it is, as I said before, most of the basic work that the microprocessor has been doing in 70s and nowadays is pretty much same, except the speed, except little bit of processing things difference, and the set of instructions. I gave you 6 pages of instructions. These are all the set of instructions we will have for this semester for the microprocessor we'll be using. Remember, in the last class I was talking about the Motorola microprocessor we'll be using in the lab, and this is the set of instruction for that microprocessor. Now again, I just want to mention that the purpose of this class is not to understand how the Motorola microprocessor works. The purpose is to understand how the microprocessor works. So, when you understand this set of instruction, and when you can write the code or modify the code or correct the code or debug the code, what happens? In future, if you have some other microprocessor or other set of instruction, you will be able to understand those using the knowledge you have learned here. That is the objective. I'm just trying to make sure you don't have nothing to do with the microprocessor, Motorola microprocessor. You may not be able you'll even never see this microprocessor anymore in probably your life. But you might see some other microprocessor. Okay. Now, microprocessor is called a central processing unit, so which is basically the brain of a computer, because it does all the operations. It's basically the central unit which controls all the operations, and we are the one who give the instruction to microprocessor through the code, because all the programs we are running, they have some kind of code, right? Even all the apps we are running in the cell phone, those are just bunch of code. So what do? You just give some instruction, and the compiler is basically decoding those instructions for you so that the microprocessor understands it. Let's say these are the instruction microprocessor understands, and you are writing the code here, okay? So everything that you understand. But what happens when you write the code, it basically decoded in several phases. At some point, the machine understands it, and this is exactly the instructions you have in front of you that your microprocessor will understand. But these are much lower than what we understand. So we need some knowledge before we look at those instructions. Trust me, all we will be doing in this semester is just to understand all those 6 pages. Everything is about all those 6 pages, okay? Most of the cases I tell my students that even after today, if you see me anywhere, don't talk to me if you don't have it, okay? Because everything we'll be talking on those, okay? Even, we had, that was something like, in the last semester I had some student, he lost it twice. And then during the test time, our tests are open book. Everything is open. You can also use the set of microprocessor, set of instructions are also open, okay? But I said the next time if you lose it, we'll charge you, and he agreed. So let's go back here. So the microprocessor have different models, like 4-bit microprocessor, 16-bit microprocessor, 8-bit microprocessor. Basically, the one you have in front of you, those are 64-bit microprocessor. The only difference between the 64-bit, 32-bit, and 4-bit is basically how big data they can use to work with. For an example, as you know that the microprocessor can only do addition, arithmetic operation. That is the only one arithmetic operation it can do, which is addition. Now the 4-bit microprocessor will be able to add 2 4-bit numbers. Okay, an 8-bit microprocessor will be able to add 2 8-bit numbers. 16-bit microprocessor will be at max a number of 16-bit. Now what happens if you have a larger number? Let's say you have an 8-bit number and you are trying to add it in the 4-bit microprocessor. It still is possible, but it takes longer time, because you know the 8-bit microprocessor will be able to handle the 8-bit data at once. But the 4-bit microprocessor will take twice to do that. It will take the 4-bit first, do some addition, and probably take the carries and start doing the addition to the other half. I'm talking about the top half, okay, or left half. So you know it takes longer. So that's why the 64-bit people, you know, at some point I think you have seen that people were running after 16-bit microprocessor, 16-bit operating system. Now these days most of the computers are 16-bit, right? I think 3 years back, all the computers, laptops we had were like 32-bit. Do they work? Yes, but they are a little bit slower because they still work with the 32-bit. So we still, you know, we want to process faster, and there are some other issues as well. It's not only about the 64-bit and 32-bit. So, and the bad news is the microprocessor will be using for our class, it will be 8-bit. So don't get frustrated for that, but you know, we're still learning how it works. It doesn't matter how fast it is. So, and all the microprocessor is just bunch of some circuits, okay? At the end, there are bunch of some circuits, but there is an integrated circuit because it's so compact. Even if you try to, for an example, you probably will be able to build that circuit in a breadboard, not one, like let's say you might need like, this table will not enough for sure. You will probably need like 10 or 20 tables, such tables to basically build the whole connections of one microprocessor, which is this small. Because that's because of the extraordinary achievement in VLSI design that people are able to integrate the circuit so small. But you know, at the end, there's the same circuit which you will be able to build using the breadboard, maybe. But you know, there might be some transition delays and some other stuff. Now, the family of the microprocessor in this class we'll be talking is M86800. You know, that is a name given by the Motorola. So that is the name of the family of the microprocessor, because you know they did not only build this microprocessor, they built several other microprocessors which are pretty much similar, and the reason they belong to the same family because they pretty much have the same list of instructions. You know, the more advanced the microprocessor you have, you probably will have a longer list. At this point, let's say you have 6 pages of instruction. The microprocessor you have inside the computer you have in front of you might have like, you know, 20 pages of instructions. So the more instructions it understands, it's a little bit better because, you know, it understands more. It will, you know, it probably can do it a little bit faster. Some operations are like integrated. Now, this is a very basic architectural design of a computer. Doesn't matter what computer it is, doesn't matter it's from 70s, still it's working in the same way. If you look at clearly here, this is the microprocessor. Let's say these are the memory and this is the input-output port. Now what happens, anytime you are working, the microprocessor is basically controlling the memory and the input through the address bus. Do you see the address bus in the left side? Now the address bus means those are all the connections of 16 lines. So what does it mean? It means that all the memory locations has an address. Each of those has an address. What do you mean by address? Let's say you have some memory locations. These are memory locations. This has an address which is, let's say, 0000. So what will be the address of the next one? You know, these are real physical address. For an example, let's say you live in Memphis, okay? Now nobody will be able to find you without your address, right? Similarly, when you have a bunch of memory locations, for an example, 8 gigabyte is a huge memory locations, but you know what? 1 byte has one single address. Next byte has another address. Can anyone here tell me how many bytes you will be able to address by 16 bits? Let me make you a little bit easier. Let's say I said you just have 1 bit. Okay? Let's make it simple. You just have 1 bit. How many bytes you can address? Only 2. One will be 0, another one will be 1. Because you cannot write anything except 0 or 1 in 1 byte, 1 bit. Can you? I'm talking about the binary because, you know, inside the computer everything is binary. Using the binary number system, you can only write 0 or 1, right, in 1 bit. Now, how about if I say that you have 2 lines of address bus? How many memory locations you will be able to address? 4, because using 2-bit, you can write 0, right? You can write 0, which is 0, 0. You can write 1. You can write 2, and you can write 3. So using 2-bit, you can address 4 bytes, right? Similarly, using 16-bit, how many? Look at the pattern. Let me show you a pattern. When you are using 2-bit, you are basically addressing this much. This is the number of bits. Okay. When you are probably using 3 bits, you will be able to address this much, which is 8, right? Because look at this. Using 3 bits, you can write all the way from 0 to 7, which are 8 total, right? So using 16-bit like this one, how many address you'll be able to, how many bytes you'll be able to address? Can anyone here tell me what is 2 to the 16? Okay, that will be probably the next homework. Okay, now we know that we have the calculator. So let's so using this, microprocessor knows exactly the address. So it basically can pinpoint which address it's talking about. Okay, and we have the control bus. Okay, control bus is not, and you see the control bus is not 16-bit. Most of the control bus is 8-bit. So using the control bus, all it does is it basically enables or disables things. Now let's say you are trying to take some input. So what it should do, it should disable all the other things except the input lines. You know what I'm saying? When you are trying to work only with the memory locations, what it will do, it will just disable everything except the memory lines. Okay? So that's exactly what it is. Now, these are some applications. I'm sure that everything has microprocessor these days. So I think this is not enough even here. So everything has a microprocessor. You might have a smart home, you might phones, home, monitor, computer, cell phone, automobiles, even the vending machine. Everything has microprocessor, but they have different speed. They have different set of instructions based on their need. I'm sure that any vending machine will not have a list of instruction of 6 pages for sure, because it will be too much, and you don't need that. Now, this is probably an idea that how the microprocessor control different things. Let me show an example here. Let's say this 6800 is your microprocessor, okay? And these are all the, you see here left side, these are all the 16 bits for addressing, okay? Now look at this. When you have a number here, what is this number? Can you read this number in binary? What is this? This 3, right? Which is this one. This is 3, right? So we can change this one to 4, then this will be the address. Let's say these are bunch of memory locations, right? Now, let's say the microprocessor is trying to read. Now, what do you mean by read? By saying read, we're saying that the data will be loaded from memory to microprocessor. Remember, inside the microprocessor, there are some special types of memory which are called register. All the operations in the computer are done in those registers. When you buy the computer, even laptop or desktop, have you ever heard something about cache memory? See, these days, even the computers are so cheap, or things are like, in GB, still, the cache memory is still in terms of megabyte. Have you seen it before? I think at this point, I can remember the fastest microprocessor had 8 megabyte of cache. That's probably the fastest we have right now, as far as I remember. I'm talking about the personal ones. Server or those things might have different, because the cache memories are the memories which are inside the processor, and those are the fastest memory locations in the world. And all the operations in your computer is basically done in those, not in the RAM. RAM is basically loading the data, but it doesn't add anything, it doesn't subtract anything. Now what happens, when you need to do some operation, all the data is loaded into those registers, and the computer does the operation. We'll show you all those over the time we'll understand it much better. But let's say, for an example, let's say microprocessor is trying to read. Now what do we mean by read? By read we means that the data will be transferred from the memory location to microprocessor, right? Now what happens? Let's say what happens is, do you see this symbol? What do you mean by this? That means if this line is high, by high, right? That's 1. If this line is high, that means microprocessor is in reading mode. If this is low, microprocessor is in writing mode. Now, what happens when it is read? When it is read, it is pointing. Now, at this point, let's say this is in read mode, for an example. This is the address. So that means microprocessor will be reading from this location. That means this byte of data will be transferred to microprocessor through these 8 lines. Do you see the 8 lines here? Now, think about carefully. We exactly have this data here. Do you see it? Look at this, 00, 11, 01, 00. That is the exact data you have. Now, to do this one loading, what do you have to do exactly? Couple of things. One is, you first have to enable the reading line. Before that, you might have to determine the address of the, because you probably will be choosing only one location, right? You have like millions of locations. You'll be choosing only one location, right? That address will be here. And then next, you'll be choosing either read mode or writing mode. Now you choose reader mode, then that byte will be here. And then microprocessor is reading because that byte is read. Now what happens if you are in the writing mode? Then again, you have to select the address. There will be some data here. That byte will be replaced by this data. Now how many steps you have here? Look at this. Several steps. But when you write just one single expression in C++, you probably cannot imagine how many times all these things are happening. But now you will feel it. Now, we'll go back to this again probably after a while. I'm just giving you some, very basic, refreshing idea so that you will just can guess. Now, these are some basic registers. As I said, that we have some registers which are extremely useful. And remember, the registers are will be varying in sizes and types based on the microprocessor. So these are the list of registers we have for Motorola 6800 family of microprocessor. Now what registers we have? Look at this. Accumulator A and accumulator B. Look at their size. They are only 1 byte each. They are extremely useful. They always load some data or they do some operation. We'll see. Okay, we'll know about those registers. But at this point, they are the fastest RAM memory locations you have inside the microprocessor. Now, these are index register, stack pointer, and program counter. They also are register. And the conditional code register, that's another one. So how many registers we got here? 6. We have some other registers as well, but these are the general one. Okay, we have some special purpose register. We'll know it over the time, but these are the generic one. So we'll be able to use it for most of those instructions. Okay. Now, just by looking at those, before we come here, just look at the slide we looked at before. From this slide, can you tell me that how long the address is going to be? Any address will be 16-bit, right? Do you see that address bus is 16-bit? The more lines you will have in the address bus, that means the more bytes you will be able to address. Let me tell you something. I'm not sure, have you ever heard it or have you ever experienced it? When you have 32-bit machines, before this one, even if you try to install 4 GB of RAM, have you ever tried it? Any 32-bit machine cannot allocate more than 3 point something. So it doesn't matter how many memory bytes you allocate, those are not usable. Why? Because any 32-bit machine, there are 32 lines of addresses, right? So that is basically this much. So it can generate this many addresses, which are not enough for 4 GB. Because you need one address for 1 byte. Think about how many bytes you have in 4 GB. What is 4 giga? What is 4 giga? In general, the giga is 10 to the power 9, right? But the calculation of the bytes is a little bit different. Okay, so even if you assume there's 10.9, so I'm sorry, the 10 to the power 9, it will be huge, right? It's not for 10 to the power 9 because 1 byte is basically 1 gigabyte is 1024 megabyte, and it will be something like this. 4 times, this is megabyte now, this is kilobyte, and this is byte. How many bytes you got? 4 times 1024 times 1024 times 1024. It's a huge memory locations, right? Which is more than 2 to the power 32. That was the reason why anything more than 3.2, your microprocessor were not able to address them. So those were unused. Okay. Now it's possible because at this point, but 64 has a limit as well, but it's much more than 32. Now, what do you know from here? What do you know about the data? How long the data is? Only 1 byte. You know, this is the architecture of the machine we are talking about, and we'll be dealing with this machine for next 2 semesters. I'm saying this semester and the next semester. Okay. Now, what do you guess from this register? Look at this. Some of the registers we have only 1 byte, right? Some of the registers we have 2 bytes. Just as a guess, the registers you have 1 byte probably will be useful when we'll be dealing with the data, because our data are 8 byte. The 8 bits, right? And the register with 16 bit will be probably useful when we'll be dealing with 16 bits. So if you don't understand at this point, don't get worried, because we'll not be dealing with everything at a time. It's just like a refresher, and we'll be doing just one baby step at a time. We'll show you the baby steps, so it will be extremely easy at this point. These are some examples of the instruction. We load something, we add something, we'll show you how to work with those. I'm not going over this because I don't want to scare each other. We don't want to scare each other at this point. Now let's start from here. This is the most important slide for tonight. This is how an instruction will look like in most of the cases. You know, as I said before, all the purpose of this semester is just to understand those 6 pages. If anybody here can read all the 6 instructions tonight and understand everything tomorrow, you don't have to come to the class by after tomorrow. All right. So, most of the instructions, you will have 2 different parts, just like this one. I picked it from here. You will find it because, you know, all the instructions here are alphabetically ordered. So you will get LDAA, right? Now, at this point, remember, we are not trying to understand what this instruction does. We are just trying to understand what we got in the instruction. What do we have? So there are 2 parts. Look at the first part. We call it opcode. For any instruction, you know, there is a plain English, right? Like I'm saying, the English letters, alphabetic letters, right? LDAA. We don't understand what do you mean by LDAA, but you know, that's plain English to us. So we just know that that's opcode, and the second part is called operand. I think that's not too much for remember, just for memorizing, right? We'll know it, right? We can memorize that. Now, what happens when the instruction is executed? What happens is, this is the assembly, okay? LDAA, pound sign or hash sign $02 is an assembly instruction. You know, we told about that, right? We are going to learn assembly. That's a low-level programming language, okay? That's in assembly, and assembly is very close to the machine code because it's just translated in one step, it becomes machine code. Now, when it translated, the opcode looks exactly the same. Do you see the opcode is still 02 and we wrote 02 here? But LDAA has a special meaning to the computer. The compiler knows it. Basically, the assembler knows it. We don't know exactly how to do this at this point. I'm just showing you an example. So the LDAA becomes 86. Do you remember anything we write here is in hex, right? So 8602 is in hex. Next time, we'll just write number. Remember, everything will be in hex unless we say it's not hex. So it's in hex. These codes are called object code. These are basically machine code. Your processor, every time I mention processor, that means a Motorola microprocessor. Okay, that processor will exactly understand what does it mean by 8602. And this is exactly what happens. Doesn't matter what code you write in C++ or Java or any other language, or even the scripting language like Perl or CGI programming or anything. Okay, whenever you're writing, but there will be a lot of decoding, and at one point, it becomes just like this. And interesting is, we are writing in hex because hex is smaller, I'm saying using only 2 digits you can write a bunch of because look at this, writing 86 in binary, it will be very long, right? So I'm saying, but inside the computer everything is binary. Don't think that computer is representing the numbers using hex. We are writing in hex because we want to understand in simple form. So the 86 can be written only 2 digit, but if you want to write 86 in binary, it will be longer, right? That's why we are writing in hex. Don't assume that the computer writes in hex. Computer writes 86 in binary, 02 in binary, okay? So, but your microprocessor understand what exactly it has to do with that. Remember those things, load it, make it, change the mode to reading mode, copy it, those things are basically instructed by your instruction. Now, at this point, we are just trying to understand something like this, because all the instructions you have in this page, I'm saying that in these 6 pages, those have some different modes. We don't understand what do you mean by the mode, okay? Just assume they have these 6, they can have at max these 6 modes. Some instruction has all the 6 modes, some instruction do not have 6 modes, some instructions has only 2 modes, 3 modes, okay? You see the list of modes there. But just by looking at the instruction, how do we know what is the mode? Because for an example, the LDA, have you seen the LDA just before this one? LDAA has an immediate mode, has a direct mode, has an extended mode, okay, has a indexed mode. Now, just looking at the instruction, how do I know, is this an immediate mode? So this class tonight, we'll just try to know what the mode is. How do I know what will be the mode of the instruction? Remember, at this point, we don't know anything basically. We are just trying to see, even we don't know exactly what that instruction does. Don't be patient, okay? Because we are just starting. So over the time we'll learn, and we'll learn. Now, for this chapter basically, we'll not be talking about the last 2 modes. I'm just trying to show you this because these are the exhaustive list of all the modes. We'll be at some point in the semester, probably sometime in the first half, we'll be basically talking about the relative mode and indexed mode. So let's concentrate only on the first 4. Immediate, direct, extended, inherent. Trust me, I have been teaching this class for the last 3 years, meaning 6 semesters. So, the book is written and they try to explain a lot of things, but I try to find something which is very basic. Just by looking at the instruction, we'll be able to tell what is the mode, even without understanding what the instruction does. Because at this point, we know nothing, okay? Now, let's look at some example or some clue, okay? If you use the clue, trust me, it doesn't matter what instruction you have, it will be working. Now, immediate. How do I know that the instruction is immediate? Look at this. Operand. Remember, the instruction has 2 parts. Opcode, operand, okay? Look at the operand. If the operand starts with a hash or pound sign, I know that you prefer to say pound sign, but the engineers prefer to say hash. Because most of the time pound signs are used by telephone operators, most of the cases. But in this class, sometimes if I say it's a hash, you understand that's a pound sign, okay? So operand always starts with a hash. That's it. Example, look at the 3 examples. Do you see these 3 examples? The operand start, see all these 3 are LDAA, but they start with a hash. So right away we know that the mode is immediate. Any question here? Too simple. Now let's look at the next one. Next mode is direct. How do I know this is direct? It will not have any hash in the operand, and also the operand will be 1 byte in length. How do I know it's 1 byte? Look at this. First of all, here, I think you can guess this is a binary number, right? How do you know that one binary number is 1 byte? It should be 8-bit, right? Not more than 8. 8-bit is a byte, right? Not more than 8-bit. So that means it's a byte. The last number is decimal. How do I know that that's 1 byte? Remember, 1 byte means 0 to 255. Anything larger than 255 you cannot write in 1 byte. 255 means all ones, 8 ones. So anything larger than that you cannot write in 8 bit. So that means it's more than a byte. And hex numbers, whenever you are writing a hex number, if there is 2 digit, just 2 digit, that means that's 1 byte. Look at the hex number here, A2, right? That means that's 1 byte. Anything you have more than 2 digit, even if it is 3, that means it's more than a byte. Now, one more clue. You see here the operand can be written in hex, can be written in binary, can be written in decimal. A compiler understand, I'm sorry, an assembler understand all of this. But how do you know if it is binary or, because you know it's very tricky, right? Binary can be decimal as well, because 0 and 1 belong to decimal, right? 0 and 1 belong to hex as well, those 2 digits. The way you understand, look at this. Decimal number has no prefixes, right? Do you see here? Binary number will always have a prefix of percentage sign, and hex number will always have a dollar sign. This is one of the class when people get frustrated just by looking at the dollar sign, because you know we always like to see a lot of dollar sign, because but this is the class is so frustrating because this dollar sign is not the real dollar. Okay, this is the hex number. Now remember, datas, operands, if it starts with a dollar sign, that's a hex number. If it starts with a percentage sign, binary. If it starts with no prefix, I should say probably no dollar sign, no percentage sign, binary. Decimal. Okay, but we also have to understand either it's a 1 byte or more. Okay. Now, how do I know it's direct mode? There will be no hash in the operand, and the data doesn't matter it's a decimal or binary or hex. It will be 1 byte. Now, extended is very close to direct. It also has no hash, but the operand is 2 byte. Look at the operand here. This must be hex, right? It starts with a dollar sign, and you see here there's more than 2 digit, right? The first one, so that must be 2 byte. It's more than 8 bit binary, and you know that's binary because of percentage sign, right? And the last one is definitely more than 255, 53,539, which is much more. Now, can you tell me how long, what is the largest number you can write in 2 byte in decimal? 65,000. You probably remember it, right? So all ones of 16 bit. Okay. All right. This is extended. One more left. Inherent is the easiest one because the inherent instruction has no operand at all. That has only opcode. Any question here? Now let's check. You see, now we'll be looking at some example. These will be exactly the same question you will have in quiz 1. We'll do the quiz 1 tonight after we are done with the lecture. Now, answer this question. These are quiz questions. You remember, you will have the same question in the quizzes, similar questions. Look at the instruction, the blue one. What is the mode? Everybody, B is direct? No? It must be immediate because it has pound sign, you know, the hash. That's the only one. So the right answer is immediate. Any doubt? Let's look at the next question. What is the mode? First of all, this is not immediate for sure, right? Because there is no pound sign. Is this inherent? For sure no, because there is operand. So it must be direct or extended, right? What is that? Direct? It's direct because the byte is 1 byte, right? Because it's less than 255 in decimal, right? Now number is decimal, right? Because okay, so right answer is direct. Let's check this one. This is an instruction. It must be inherent, right? That's the easiest one because no operand. Okay, inherent. How about this? Extended, because it's more than a byte, right? In hex. All right, it's extended. How about this one? Everyone extended? Are you sure? See, at this point we don't understand the instruction, but we are just trying to understand the mode. So this is extended for sure, right? Yeah. Let's try this. It should be direct, right? But it's not. Oops. Because there are exceptions. Now, remember, it looks like, according to the formula or the rules we know, it should be direct, there is no doubt. But you always want to check with the set of instruction. Check the NEG there. It should be in order, in alphabetic order. Check the NEG. Did you find NEG there? Look at how many modes are available there. Did you find NEG? You don't have NEG?
Yeah.
What modes you have there?
Extended and indirect.
So it does not have the direct mode. So remember, this is an exception. That's why I gave you this example and I wrote it in red line. So that means there are some instructions which will look like direct, but check with your set of instruction always before you answer, because some instructions do not have direct mode. If it looks like direct, but it does not have the direct mode, that means it will be falling into extended mode. That is an exception, okay? So before you answer the direct and extended, check with the set of instruction. You know, let me tell you this. You probably can ask me why. Trust me, I'll answer this question. But we are not ready yet. Okay? Because, you know, we don't understand what this instruction means, okay? So, you know, over the time we'll understand it, why it does not have direct mode. But at this point, we just know that before we answer the direct mode, always we want to check, okay? Now, look at this. We are not done, but your slide is telling we are ready for homework 1. So that's exactly you will see in this lecture. In several points, we'll stop, okay? So this is the point we'll stop for tonight, and next lecture will start from the next slide, which will be covering, of course, the next homework. And also, you also want to make sure that you will get 65% in homework 1 so that you can see the next homework. Now let's log on to pause and go to the homework. I think you're almost ready for the homework because you just answered all the question and you have understanding and you know the exception as well, okay? Any question?
The exception only applies to
Direct. It looks direct. Be careful about the direct. That will be the only point you should make sure, because the direct will not be direct if it is not in the set of instruction. Then it will be extended. That will only apply to the direct kind of instruction. The other ones will be, you know, right away you'll know it. Any other question? So let's stop here for tonight.